All right, it looks like we're live now. So welcome everyone. In this session, we have Niveditha Kalavakonda, Ph.D. student in Electrical and Computer Engineering departments at the University of Washington. And she's going to be presenting a talk on the role of computer vision in revolutionizing computer-assisted surgery. Just a quick note, please post your questions in the Q&A section instead of in the chat. And Nivi, reminder to start your timer. Off to you.
Awesome. Thank you so much, Kristen. So hi, everyone. I'm Niveditha Kalavakonda. I'm a PhD student at UW. Like Kristen mentioned, I work at the BioRobotics Lab in the Electrical and Computer Engineering department. I'm primarily advised by Professor Blake Hannaford and Dr. Laligam Shaker at the University of Washington School of Medicine. I'm also fortunate to be a part of the Tech Policy Lab located at the Europe School of Law. I am advised by Professor Ryan Calo to look into essentially policy matters that and the space of robotics and machine learning. I'm really excited to be here. So this talk is going to cover some of the projects that we worked at, the BioRobotics Lab on. So this work is not just something that I've spent a lot of time on. It's also it's come to fruition due to a lot of support from my peers at the BioRobotics Lab. So a picture of all of the really cool folks that I get to work with right here. With that said, let's kind of get started. This is just something that I want to make a quick note about. There is some level of like gore involved. I mean, it's probably not too bad. I tried to be as mindful as I can with the amount of like visuals that I introduced into this presentation that contain surgical but that said, there are some images that may make you uneasy, especially considering all of you are looking at this directly on your laptops and monitors. So just wanted to give you a little bit of a heads up. So if that's something that makes you uneasy, I'm sorry in advance. All right, cool. So with that being said, I'll get started with kind of what the world of computer-assisted surgery looks like, and how those of us who work in the field of data science or the adjacent field of computer vision, how can we contribute to this space? So there are a wide array of projects that exist in the computer-assisted surgery realm. So this could look like 3D modeling of internal organs from your CT or MRI scans. It can look like retinal images being used for identifying if there are certain health conditions that exist in said individuals. So for example, a project that is really famous due to the amount of PR that it's gotten is the diabetic retinopathy project that comes out of the labs at Google. Another space that, that's something I work in, my lab works in, and is very close to us, is the field of surgical robotics. And then you also have medical imaging and the broader space of like, trying to identify health conditions from, ultrasounds and x-rays and any kind of like pathology-based images as well. So what does the field that I work in specifically look like? So what I wanted to do is just show you folks a quick video of what, broadly robotics in surgery looks like, so that there's some amount of context to what we're going to be talking about. So here's a quick video. It's less than a minute. So I'm just going to play it, hoping that the sound is also coming through for you folks. Please let me know if it's too loud by any chance. The stop is a little bit abrupt. Apologize for that, but that's because there's a lot more of surgical procedures that that the video moves into. So I tried to kind of cut that off before we move in. We have to see that. But yeah, basically, the reason I wanted to show that specific video was because it shows the amount of visual data that we can get from an operating room. So there are different types of surgical robots, and then I will kind of talk to you specifically about what we are interested in, what we've been working on. So broadly, people talk about it as existing within three different categories. One is passive robots, which primarily just sense and identify what exactly is happening in an environment and then take appropriate action. So a part of the video that you just saw showed how, for example, if there's a lot of precision involved with drilling holes or inserting screws and pedicles, we can do that using a robot. So one of those category of robots basically are passive robots, for example, Robodoc, used in hip replacement surgery. And then a second category would be active robots, which is similar to the one where you see the image here to the right, where the surgeon ends up controlling what happens on the robot end. So the image inserted here is basically that of Da Vinci. And then we have a very similar surgical system that we developed at UW called the Raven. And then the third category would be semi-active, where the surgeon basically tells, decides or approves of a certain plan that a robot has possibly drafted. So Neuromate is a classic example of that. So this is the Raven 2 that we've developed here at the BioRobotics Lab. This robot is a teleoperated robot. It was not designed to work on humans. This is just a research test bench. And with this robot, what we're able to do is basically test out the different algorithms and prototypes that we are interested in building. And when I say teleoperative robot, what that specifically means is, oh yeah, this is just a cool picture of our robot at Ender's Game. If you've seen the movie, or if you plan to see it again, just make sure you pay attention to the robot that comes in the movie. But yeah, with teleoperation, what I specifically mean is the surgeon sits at a console and controls what exactly happens at the robot side, at the robot end, which is basically inserted into the patient. So in this case, I'm just showing you an example of what that looks like in a simulator. But imagine the arms basically being inserted into the patient so that whatever motion that the surgeon does at the console is translated into action at the patient end. And it helps with, dexterity, it helps with precision, it helps ensure that, if there's any tremor that's introduced because of the surgeon's movements, we're able to kind of eliminate some of those actions as well. So I've given you a bit of an introduction to the hardware that we end up using. So what I'd like to now move into is specifically talk about what computer vision in surgery looks like. And I'm going to touch upon quickly 3 different projects that we have at the lab that I think kind of define broadly the really fascinating trajectories that computer vision will lead to down the line for computer-assisted surgery in general. So the first category is where we end up tracking motion so that we're able to compensate for that motion just based off of the data that we get from a camera. So one of the projects that we did is one where we simulated the beating heart of a cow, and we were trying to track blood vessels and eliminate that motion while showing the view back to the surgeon. So why this is important is because when we are operating on the surgeon is directly operating on a patient, they are able to kind of see the breathing movement of the patient and compensate for that directly when they're operating on said patient. But now with the teleoperative system, the surgeon is going to be sitting away at a console, whereas there's only a camera and end effectors inserted into the patient. So what we want to do is basically try and eliminate some of that motion that the surgeon is not able to actively see and perceive, and instead like see how we can automatically just remove or compensate for that motion so that the surgeon can just directly focus on the surgical procedure at hand. So this is a video where, the KUKA arm that we're seeing here to the right is simulating the motion of a beating heart that we were able to record. And it's just replaying the motion of a beating heart. And the image that you're seeing here is that of a blood vessel. And what we're trying to do is track the motion of that blood vessel and have our robot end effector compensate for that motion actively, so that when the surgeon is operating, all they need to worry about is directly perform the action that is of interest and not have to like actively also compensate and be concerned about like what is happening on the breathing, happening because of the breathing on the patient side of things. All right, I'm going to go on to the next project. And these two are projects that are pretty long term. These are ideas that people have proposed and people have talked about for a while. But fortunately, now that we're more, integrating more of deep neural networks and, having ways to bring together a lot of data, a lot of patterns, and identify how we can incorporate that knowledge into robotics, we're seeing some amount of advances, or leaps. I won't necessarily say leaps and bounds, but we're definitely seeing a good amount of progress in the space of like haptics or bilateral teleoperation, and moving more into automated systems for surgery, automated subtasks within surgery. So the project here down below, it talks specifically about how we're able to incorporate the information that we get from camera to identify how we can translate like movement into force information and hence haptics within surgical robotics. So like I was saying, the surgeon currently sits at a console, which is basically displaced from being near the and hence the initial action of like directly operating on the patient and getting that sense of touch is lost for the surgeons these days. So what we're hoping to do is basically use the information that we're getting from cameras and see how we can track the deformation of tissues and translate that to force estimation, and hence identify what amount of force feedback we can give back to surgeons. So the way this is done is there are cameras that are directly capturing the information that's, the surgical space, what's happening inside the patient. And with that information, we're able to see how much a tissue, for example, deforms. So by developing mathematical models, we're able to translate that definition into a force estimate and then generate haptic feedback so that the surgeon gets a sense of touch when they basically press their instrument against any kind of tissue. So another project that is of great interest to us, and I'll go into a little bit more detail right now, is basically collaborative surgery. So the way you can think of collaborative robotics is try and see like how we can have a surgeon and a surgical or robotic assistant work in the same workspace. So for this, what we need to basically understand is identify and track where the surgical instruments are at all points in time, create an intuitive interaction interface between the surgeon and the robot, and also perform one of like the most repetitive tasks that we've observed that human surgical assistants tend to perform, which could be the suction, grasp, or pull. So here is an example where there are surgical subtasks that are entirely automated. This was a project that was in collaboration with UC Berkeley.
This is linear debridement, removing a linear section of cancerous tissue. Tissue phantom. A computer vision system identifies the linear section and guides the robot to extract it in subsections. In 5 trials, the robot successfully extracted all target tissue in pink. The next subtask is spherical debridement, removing a set of randomly placed spherical sections of cancerous tissue. We use plastic putty as a proxy for healthy tissue. Embedded in the healthy tissue are multiple targets made of the viscoelastic material shown in pink. These targets represent damaged or tumorous tissue. A computer vision system identifies the target spheres and guides the robot to extract them. In 50 trials, the robot achieved a 96% success rate. This subtask is from a laparoscopic surgeon's training kit, cutting a circular pattern from a sheet of gauze. A computer vision system identifies the circle and guides the robot to cut along the lower and upper halves. The second gripper stretches the gauze, while the first gripper cuts the pattern. In 20 trials, the robot achieved a 70% success rate with a 99.89% cutting accuracy in successful trials. The video is sped up by a factor of 8. The robot is currently half as fast as human experts. However, not all trials were successful. We show here failure modes of this subtask. We are working to improve robustness for future work.
Sweet. The video that you just saw talks about completely automated surgical subtasks. And one thing that we took away from that is also trying to identify how, instead of having a robot, moving directly to a fully automated setup, how can we have a surgeon and a robot interface and have the robot just perform assistive tasks? And so, with robot-assisted surgery, we're able to improve precision. It enhances safety of our interventions. And when we have instrument tracking, for example, in addition to benefiting the semi-autonomous surgery, it also has myriad benefits, including visual soloing of robots. We're able to see, for example, if there are any potential instrument collisions, we'll be able to track that data. We'll be able to identify what phase in a surgical procedure, a certain video is. Then any kind of interventional workflow analysis, trying to identify, what level of expertise a surgeon is just from video. We're able to do all of those things if we can identify and track surgical instruments within the field. So this, unlike automated surgery where we only have the robot, we don't get the information for where the instruments are at all points in time, because we no longer have those robotic encoders tracking where those instruments are at all points in time. So for that reason, that's kind of where computer vision comes into play. And we're able to try and identify where exactly these instruments are, just based on endoscopic or microscopic camera input. So what you're seeing here, for example, is endoscopic robotic instruments that were segmented, and we're able to get a lot of data, including whether something is an instrument or not, what type of instrument it is, and for each instrument, we can identify what is the shaft, what is the wrist, and what is the end effector. So, we're able to I'm going to go through this a little more quickly, I guess. But so I can see, when I take a classical computer vision baseline where I just use a heuristic-based approach, I can see in comparison to using more recent types of methods where, like, for example, we used a unit-based CNN, there's a significant performance jump. And we started seeing what type of benefits we can get by incorporating deep learning into a lot of this surgical analysis, surgical data analysis that we're able to get. So in this case, you can see a classic case of a performance jump. A heuristic-based method, for example, for the neurosurgical instruments, we saw a DICE coefficient of 0.339. And in comparison to that, when we use a unit-based CNN, we're able to see almost twice, if not more, of a jump when it comes to performance. So another case, of another use case where computer vision comes into play is making use of active learning for surgical instrument segmentation. So in this case, when we have a lot of these instrument data that we're collecting from the operating room, we don't necessarily know what type of data would be most useful for our model, as opposed to just sequentially segmenting data and feeding all of it. Data segmentation is extremely expensive, and having surgeons basically is even more expensive because expert time, as you can imagine, is extremely pricey. So having surgeons annotate data that that the model would find most useful would be the best use of everyone's time. So for that reason, we made use of this concept of active, and we essentially had a Monte Carlo dropout type of setup to identify epistemic uncertainty. And once that uncertainty is estimated, we try to see which instances had, which instances the model was the most uncertain about. And once we identified those instances were then sent to the human annotator instead of sending all of the instances. Because as you can imagine, some of the data, some of the images basically giving us redundant information. So we were trying to identify which instances were our model most uncertain about, and then have our human annotators basically give us the labels for those, and then train the model again. So with that, we were able to see, in some cases, even just using 60% of the data was able to get us to that peak performance instead of having to use all 100% of the data while we were training. So those are some of the benefits when we use methods like active learning, not just for fields like natural language processing, but also useful in surgical visual analysis. Another trajectory we're taking is basically trying to identify where the instrument is and predict where in the future or in the next 5 frames, for example, where will the instrument be. So that's another trajectory where computer vision will be very helpful for computer-assisted surgery. That said, I'll kind of wrap it up so that we can open it up for questions. These are some of the future directions that we're currently looking at. So as you can imagine, the medical field, the medical space in general is very data scarce. There's a paucity of labeled data. So what we're trying to see is if we can use techniques like self-supervised learning, how can we take advantage of all of that data that we're collecting from the operating room to extract patterns so that we can only fine tune on a smaller subset of data instead of having to label a large volume of data. Another trajectory that we're looking at is looking at interpretable models and identifying how we can create a surgeon system trust and classify what are the different trust modes that we can have a human and a robot collaborate together with, or in this case, a human and an AI model collaborate together with. We also would like to kind of move into the actual collaborative robotics aspect of things, so that we're going to take the instrument tracking models and use it to evaluate user intent and perform collaborative suction tasks on the Raven 2 surgical robot at UW. That's it. Here are some of the references, and I think we'll open it up for questions. I'm going to stop sharing my screen so that I can see what's going on.
Great. Thank you for a great talk, Nivi. That was really exciting. It's very cool to hear about these applications. I'll let you take the questions from here.
Sweet. Yeah, that sounds good. So one question basically talks about, you mentioned NLP. How is NLP used in healthcare? That's a great question. So one of the classic examples that we see NLP being used is in electronic health records. So a lot of the surgeons tend to take notes of their interactions with patients, and all of those notes tend to contain valuable information for us to then extract patterns from. Also, when a doctor comes and pays attention to visit a patient in their room, for example, they also make notes. Those notes are also very useful to help track which patients could possibly be most at risk. So that's some of the use cases where we're seeing NLP being used. What types of computer vision applications are currently in use in healthcare? That's a great question again. So one of the things that we're seeing is a lot of surgical data analysis or data science is now becoming a subfield where you are able to generate a lot of information from the operating room. How do we now best make use of the data that we're collecting in the operating room so that we can provide either assistive guidance to surgeons? So, for example, these instruments that we're tracking, we can also create overlays. We can create 3D overlays for surgeons to then try and identify, where a certain instrument should be placed or where an organ, for example, could be hidden. We can have cameras that are directly pointed at the patient and try to identify where the organs are. And then a 3D overlay would also help us to, ensure that we don't rupture any of these organs by mistake. And then, so basically there are any number of use cases. Another is surgical phase analysis, or, trying to identify which phase in a surgery a certain video is showcasing. And you can also have these surgical phases then be used to extract like a 3-minute highlight video. So something that surgeons do these days is for their residents, they'll give a very short 3-minute version or a 5-minute version of a certain surgical procedure for the residents to reference. We can automate that entire process by basically finding the most interesting key frames and then stitching those together to create those 3-minute videos. So think of it like a sports highlight, but for surgery. So those are some of the use cases where we're seeing computer vision being useful. And then one other question is like, how does the robot success in surgery compared to conventional surgery? That's a great question, because one thing that we're noticing is robotic surgery and conventional surgery, success rate wise, they're not very different from each other. So we're not seeing a ton of benefit because of like success of a surgery. But one thing that we are seeing is patients tend to have less scarring and hence heal a lot quicker during robotic surgical procedures. Whereas for more conventional surgery, surgeons tend to create larger incisions, for example, that tends to take longer to heal, and patients tend to be admitted for a longer period of time. So that's one of the key differences that we're able to see. And there are benefits to the surgeon as well, which involves, more increased dexterity and reducing the tremors in the surgeon's hand movements. So those are some of the benefits that are provided to the surgeon.
That's really cool. It's interesting. Yeah. Cool. Awesome. Well, I think that's all we have time for today. So let's let you guys go to the next sessions. We have a lot of other sessions coming up right at 11. And if you want to reach out to Nivi, I did post her email address in the chat, or you can send her a message on Excelvents. So great.
Yeah.
Thank you
so much. Thanks, folks.